All right, so we know how to figure out what type of function would be appropriate for data. So let's look at a real world example. The owner of a framing store tracks the cost of bubble wrap packing pictures like the one shown. How can you use the data to estimate the cost of the bubble wrap for a picture with a length of 75 inches? So we're going to take a look at the data he's collected. We're going to come up with a function that models that, and then you can use the function, the model, to predict anything. We're going to try to estimate the cost of 75 inches because he does not have data for 75 inches, but he'll be able to predict what it will be. So our first step is to determine whether a linear, exponential, or quadratic function models, or which one of those would best represent the data. So why don't we extend our table so we can work on finding the differences to see if we have first difference, second differences, or the ratios that are constant. So let's do our first differences. Well, before we do that, let's make sure that our x values are increasing by a constant amount. So we're going from 6 to 12 to 18 to 24 to 30. So that is a constant increase. Our x values are increasing by 6, and that's consistently increasing by 6. So that's okay. It doesn't have to increase by 1 every time as long as it's a constant increase of your x values. All right, so we're going to find our first difference. We take our second y value, 0.31, and we subtract the y value before it, 0.10, and we get 0.21. Now we take our 0.62, subtract the 1 before it, 0.31, and we get 0.31. Now let's take 1.04 and subtract 0.62, and we get 0.42. And then 1.57, let's subtract the 1.04, and we get 0.53. So if we look at our first differences, are these constant? And they're not. They're far enough apart in what we're looking at. So this tells us that it's not linear. So let's find our second differences to see if we might be looking at a quadratic function. I'm going to extend my lines because I didn't draw them long enough. There we go. Okay, let's find those second differences and see how that looks. So we're going to we're finding the differences of these. Go to the second one, that 0.31, and subtract the 0.21 before it. That gives us a 0.10. Then we'll take our 0.42 minus a 0.31, which is 0.11. Now we can see that those are not the exact same, but let's just keep going and we'll talk about what we're noticing. So 0.53 minus 0.42 is 0.11. So these are not exactly the same because we have a couple 0.11s and a couple 0.1. The difference here is down to like hundredths. So we're going to say that the second differences are roughly constant because in a real world situation, they may not be exactly constant the entire time, but as long as they're pretty darn close, I think we're good. So the second differences are, and we'll say roughly constant. We'll make that note that we recognize it's not exact. So a quadratic function best models the data. That word says data. Okay. So once we figure out that a quadratic function best models the data, now we want to write a function that represents the data. So how do we write a function if all we have is a table of values? Well, that's what we learned in our previous lesson. We're going to do a quadratic regression on our calculators, on our graphing calculators. So I have a video showing how we do that. So let's take a look at that real quick. All right, we did our first difference, second differences. We found that our second differences were roughly constant. So a quadratic function will best model the data. So we're going to use our graphing calculators to do the quadratic regression. So we go to our stat button. We're going to edit. That's where we enter in our table of values. L1 is our x coordinates, L2 is our y coordinates, so those are the ordered pairs horizontally. So I already entered those in. To do a quadratic regression, so to get a quadratic function that best fits these ordered pairs, we go back to stat, we arrow to the right, we want to calculate, and then it's option 5, that quad reg, that's quadratic regression. We come down here, we hit enter. We want to do a quadratic regression from list 1 and list 2. So we just enter through these. We want to calculate that, hit enter. And now they are giving us, here's our standard form, y equals ax squared plus bx plus c. And then they're giving us the a, b, and c values to plug into the a, b, and c. So we'll write that down after this. Just a quick reminder, our r squared is 0.99999. That is really, really, really close to 1. So this is a very strong quadratic function to model the data. So remember, the closer this number is to 1, the better representative the function is for your data. All right, so I'm going to just kind of move this out of the way a little bit. And we're going to write that equation with the a, b, and c. So what's an equation that represents the data? Y equals ax squared. Our a, it's a really small number. We're going to use 0.00, and then we're going to use four more numbers once we get to the numbers that aren't 0. That'll give us a more accurate estimate. So 1488 x squared plus our b value is 0.00, and then we want 4 numbers, 7595. X, and then plus our c value, so 0.002. So there's our function that represents the data. Step 3, substitute the x value into the equation. So we want to estimate when a frame is 75 inches long. So we're just going to plug in a 75 in for x. So we've got this to write in again. Y equals 0.001488. Parentheses, plug in a 75, square that, plus we have a 0.007595 times 75, and then plus a 0.002. We grab our calculators and we type that in very carefully, and we get 8.94. So what that tells us is that it will cost about $8.94 to wrap the picture.